Mm-hmm.
Okay, so hello everyone. So today this is our first efficient AI seminar talk, and we're very glad to invite Professor Yanzhi Wang to give us a talk. And let me find your. Professor Yanzhi Wang is currently assistant professor at the Department of ECE at the Northeastern University, and he received his bachelor degree from the Tsinghua University, China, and a PhD degree from the University of Southern California. And his current research interests mainly focus on the model compression, platform-specific acceleration of the deep learning, and he already published tremendous journal and conference papers, and I think he's the first one who had the publication in all the top computing hardware conference and the top machine learning and AI conference. And his citation has already above 8,000 times. He received the several best paper award and top paper awards, and he received the U.S. Army Young Investigator Program Award and several other awards. So now let's welcome Professor Yanzhi Wang to give us the talk towards the best possible deep learning acceleration on the edge, a compression-compilation co-design framework.
So thanks a lot for the introduction. Let me start our presentation on our work. So this is in collaboration with the College of William and Mary, and then our system is called the CocoaPi. So if you're interested, you can search and see on the YouTube or Bilibili, whatever. Okay, so deep learning is everywhere, but this is needed to say, but not everywhere enough, because I mean, it is still difficult to deploy the deep learning in the everyday device because of the power and energy and the computation requirements. So current deep learning models have a large model size. So this is clearly a challenge. It is projected that at least for the inference phase, or maybe online learning, for the deep learning systems will be deployed in the low power embedded systems. But the actual deployment actually requires to have multiple sensor inputs, like for the auto driving or the UAVs. It may have the camera sensors and maybe multiple cameras. It maybe also have the LiDAR, the audio inputs, and so on and so forth. And then this is a multimodal deep neural network with multiple inputs, and each input can be quite large in the size, like 1K by 1K or 2K by 2K. So overall, it becomes a multimodal complex neural network, which is maybe tens of times larger compared with ImageNet. So really compared with this kind of real world scenarios, the ImageNet is like a toy. But even though this kind of applications are very challenging, so this kind of systems have a very limited form factor and power budget. And also it needs to satisfy the so-called real-time performance requirement. Real-time means that it needs to finish in the order of tens of milliseconds. It cannot go to hundreds or 1 second, and that is too dangerous. People will think that, I mean, the speed is not enough, and this may cause some damaging issues, or it cannot keep pace of the video, and so on and so forth. So this is a reason that people are working on the deep learning hardware, including the GPUs, FPGAs, and many of the emerging technologies and devices. And we were also working on the hardware, but maybe not now at this moment. Here are the hardware that we previously have worked on, like the stochastic computing based, and also worked together with Dr. Yuan here at Rutgers. And then we have together worked on the neuromorphic computing, worked in something like the processing memory stuff, and the analog neural networks. So some of them is published in GSSC and maybe some other primary, the circuits, conference, and journals. And here are some of the tape outs that we have to work together on the so-called block circular matrix. Actually, Dr. Yuan.
Hi, Yanzhi. Hi, I have a question. So right now, are you changing the slides? Because right now we can only see your first slide.
Oh, I'm keeping changing the slides.
Oh,
okay?
Right now, from my screen, I can only see your first slide.
I mean, can you see I'm changing to next?
No.
Oh, then this is a problem. I mean, the system is surprisingly difficult. Then maybe, so you cannot see it. I'm changing it.
No, no, I can't see that.
Maybe you can. Maybe you can. You should do it. Thank you. Sorry.
Okay.
Maybe you can.
Yes. So can you send me your slides?
I already sent you. I think you have.
But I don't receive that.
Oh.
Or maybe you can send me via the PDF file.
I think it stops. I don't know why. I don't know why it stops. Sorry, my problem. I think I will delete some of the widgets and send to you. A smaller version. I'm deleting some of the widgets and send you a shrink. Yeah, I deleted. My problem. But actually, I used this system before and didn't encounter this kind of problem.
Oh, because right now I'm using the WebEx events, but not the WebEx meeting. I'm not sure whether there's some difference.
Okay, so maybe I'm sending it to you. Maybe it takes why it is so large. Sorry, my issue is sending to can you download it? Can you download it here?
Download from?
Yeah, from my because I have already shared here. Can you download it?
There's no option for me to download.
It's keeping sending. I think in 2 minutes will be okay.
I'm still waiting.
No, I resend it again. The connection here at home is not very good.
I think maybe you can also create a PDF version and also send to me, because I'm not sure whether it is a problem of your file is too large.
No, it's keeping sending. It's keeping sending. But it is. I know that it is too large. I'm trying to generate a PDF. Let's see if I generate a PDF. No, many of those. It's not very convenient if I generate a PDF. So I will try to remove the demos. Try to remove as much demos as I can.
Okay.
Not very. I think I think we cannot remove too much. I don't know. I think maybe some of the pixels are also large. He didn't care about this. I think maybe after a couple of minutes. Sorry.
Let me try to find whether I can assign to the host or.
Yeah, if you can assign me to the host. Sorry. Can you assign me to the co-host?
Yeah, I think right now, you are the host. Can you share screen right now? We'll also assign you to the presenter.
Also assign me to the presenter.
Already assigned to the host, so you should be able to share your screen. Can you try that again?
This still didn't have this option.
Oh,
I don't know why. I still don't have this option.
also passing the presenter to you, privilege to you.
Oh, now it's okay. Now it's
okay.
I need to be the presenter. Sorry.
Okay, that's great.
Difficult.
Sorry, that's my fault.
Not this one. Sorry, okay, I need to this one. Can you see this? Can you see the screen?
Yeah. Right now, I can see
it. Actually, I mean, full screen. Can you see the screen?
Yeah, we can see the screen.
Okay, I'm clicking. I'm changing it to another path.
Okay.
Okay.
So
this is hardware, and that's good.
Yanzhi, hold on a moment. So I may reclaim the host role. So I think you're still the presenter because I need to do the recording.
Yeah, sure. You can.
Okay.
Yeah, sure.
Okay.
Here are the kickoff. We have been working on the processing memory and stochastic computing. And then here are the work that we have done on the block circular matrix, and also the with pruning and with quantization, and summing together with Professor Yuan here. So maybe, so Bo, can you please mute yourself? There is echo. Okay, sure. And besides this, and then we have also been working on the superconducting circuits. This is together with the Yokohama National University at Japan. And then actually we have built the first deep neural network accelerator using the have built some other things like the fast Fourier transform processors. So the good thing here is that theoretically it's called zero power consumption, but in fact, because it requires cooling, so it is very difficult to say. So our current mission, we're not working too much on the hardware design these days. We were focusing on the off-the-shelf mobile devices, like the mobile phones, like the microprocessors, or the auto-driving systems. I mean, because those kind of mobile devices are anywhere used in most of the places. And then our goal is to achieve real-time performance for all deep neural networks. So conventionally, people believe that this requires server or it requires dedicated hardware accelerators. And we say, no, may not be the case. Actually, we can use the off-the-shelf, the commercial devices like a mobile phone. And our goal is to achieve the real-time performance without accuracy sacrifice on all of these systems. And our technique is so-called CocoaPi, or the compression-compilation co-design. So there are many deep neural network model compression techniques. One of them is actually weight pruning. Weight pruning has been investigated for 5 years, and the early work used the so-called non-structured weight pruning. That means that arbitrary weight can be pruned. But there is actually limited actual deployment because it is irregular. So if we want to store this system and do the computation, one weight we need to index the next weight. So the compression rate and also the computation is very much limited. So this is the limitation of this technique. To improve on this, many people work on the structured weight pruning, like we are going to eliminate the whole filters or whole channels. So if we are going to see on the structured pruning versus the unstructured, so structured pruning eliminates the whole rows, whole columns, or whole filters, whole channels. So the remaining computation can still be parallelized on the hardware devices. But the problem here is that because it's too much coarse-grained, so actually it results in certain accuracy loss. So there is also weight quantization. Weight quantization work includes binarized ways, ternarized ways, two-power ways, and so on and so forth. So this may be hardware friendly, but this may be used in the FPGAs or ASIC. It's a must to do there. But the thing here is that actually, if we're targeting at an off-the-shelf general purpose device like a mobile phone, actually weight quantization is supported to a very limited extent here. Like the mobile CPU actually can only support up to 8 bits. And then for mobile GPU, it doesn't support quantization, only supporting floating point. So this is a reason that weight quantization has limited uses and limited optimization potential in this kind of general purpose devices. And there is also weight clustering that we are going to make the weight cluster into floating point numbers. This is almost not useful these days because the computation is not reduced. And also some of our prior technique, like the block circular matrix, that we are going to make this neural network into different blocks and then for certain structure, like the circular matrix in each block. The thing here is that we want to find a unified framework to solve these problems first. So our motivation to use a mathematical solution framework, ADMM, is as follows. We found that both the weight pruning and quantization, it looks very different, but actually they can be unified into a uniform framework, which is the general clustering problem. And then it is compatible with this ADMM. So we say with pruning, we're going to cluster a number of weights to 0, and the rest of the weights can take whatever values. So this is essentially clustering. If we see the weight quantization, then this is to cluster the weights into the fixed predefined quantization levels, also clustering. Even the block circulant can be perceived as clustering because, as we can see, we're going to make these weights into different clusters, and there is like the red one in one structure, in one cluster, the green one in one cluster, and the purple one. So it's like each cluster has a certain structure inside. So the motivation to use ADMM is that it is an effective mathematical optimization to decompose an original problem into two subproblems. If we consider an original problem fx plus g of x, we are going to find this x. So this is in ADMM. We are going to first rewrite into fx plus g of z, subject to the constraint x equals to z. So this looks not necessary because if x equals z, then the solution is the same as before. Then why do we need to do this? Because through ADMM, we're going to decompose into two subproblems, one in x, another one in z. And then they are going to be solved iteratively until convergence. The first subproblem is minimize f of x plus a quadratic term q1 of x given z. So this subproblem we are given z, and then we're going to find x. Because this q1 is a quadratic function, so this subproblem has the same complexity as the original f of x. If we see in the weight pruning and quantization, the first subproblem is given by here. The first term, this f, is a loss function of the neural network. And the second is for pruning, and the third one is for the quantization. And we're going to find the w, which are the weights. So this is actually a regularization problem, and it should have the same complexity through stochastic gradient descent as the original neural network training. This is the first subproblem. For the second subproblem, we are given x, and then we want to find z. We have another term q2, which is given x, find z, which is also a quadratic function. Then is the key for the clustering-like problem, because for the clustering-like problems, there is optimal solution. We see for the weight pruning and quantization. For weight pruning, here we are given w and we find z. This is for weight pruning, and we are given w and we find y for weight quantization. And both two has polynomial time optimal solution, which is Euclidean mapping. Theoretically, there is optimal solution here. So actually, we found this optimal solution through the Euclidean mapping, which really has no intellectual merits here, because in theory, there is optimal solution in these cases. Then we have found this z and the y values through the second and the third subproblems. Now we go back to the first one. Z and y are already given, and then we regularize, and then find this w again. So this is essentially a dynamic regularization procedure. So the regularization target is going to be dynamically changed in each and every iteration. Then the question here is that someone may ask, to use regularization to find for sparsity, this is not your invention. I mean, prior work, there is L1, L2 group lasso to find for regularizations, but then what's the difference between your work and the prior work? Why your work, you can claim that to be outperformed the prior work? As we can see, you can find regularization here on the, to penalize all the ways and then trying to find for the sparsity. So what we want to point out here is that maybe if you want to prune only 10%, 20% of the ways, it's maybe okay. But if you want to prune 5 times, 10 times of the ways, then this is very damaging. So actually, the conventional regularization is not the same goal as to finding for sparsity, because it's going to penalize all the ways, even after convergence. This is not the goal for pruning. For pruning, suppose that we're going to prune by 10 times. We're going to remove 90% of the ways, but the remaining 10% of the ways, they want to increase in their magnitude. They cannot shrink in their magnitude. Otherwise, how can they compensate for the effect that 90% of the ways are already 0? But if you are going to use this kind of fixed regularization, and then those ways will keep having this penalty, and this is the reason of the inaccuracy. On the other hand, because we are a dynamic procedure, so as long as 90% of the weights are already 0, the remaining 10% of the weights will be totally flexible. So this is a reason that we have a significant gain compared with the prior work. Because this kind of work starts from LXNet, so we see this LXNet again. Now, because there is batch normalization, we have the PyTorch. So the starting accuracy shouldn't be 80% as top 5 accuracy anymore. We should go to 83%, 84, or even 85. And we see from this example, the x-axis, the y-axis is the accuracy, and the x-axis is the overall pruning rate. By saying that with almost 100 times weight pruning rate, it means that only 1% of the weights are remaining there. And then our accuracy is still okay, while with 64 times weight reduction, our accuracy is almost the same as the prior work starting accuracy. So because of this large gap, so it clearly shows our advantage. So here is our benchmark for testing. Before going to more details, actually we start from the simplest benchmark, which is the MNIST dataset. For this MNIST dataset, actually our example, we can make 99% accuracy with 700 pruning rate. It means that there is only 0.14% of the weights that are actually non-zero, and all the remaining are 0. So there are only 600 remaining weights, which is even fewer than the input pixels, because the input pixels is 28 by 28, which is 784. So suppose that we consider linear regression. Then we need to have one weight for one input. So we can see that our number of weights is even smaller compared with linear regression, but our accuracy is still 99%. So to be honest, it's very difficult for MNIST or LeNet to be lower than 99%. It's really very challenging to be lower than that. Anyway, So we see the results on VGG and the results on ResNet, and then we can see that for example, with ResNet, we can have 19 times pruning without accuracy loss, or 17 to 80 times to 20 times with less than 1% accuracy loss. So if we see the joint with pruning and quantization, we also see this LeNet, AlexNet, and ResNet. Then we can see if we considering this LeNet on MNIST, we can simultaneously reduce the number of weights by 700 times, and meanwhile using 3 bits for weight quantization. The overall model compression size is 6,645 times without accuracy loss. So this is 2 orders of magnitude higher compared with the prior work. If we see the rest of the results on AlexNet and ResNet, we can see that it is also 100 times to 300 times reduction in the model size. So we see the clear advantage here, but we have finished here in 15 minutes. The reason here is this is not enough. This is far from enough, because using the off-the-shelf mobile devices, we cannot achieve the real time using this kind of technique. First, weight quantization is very weakly supported here, and also the weight pruning, because this is non-structural pruning, is very difficult to achieve effective acceleration. So what is missing here? It's very difficult to achieve real-time execution using the above technique, although it seems very promising. If we take one specific example, like YOLO V4, which is actually on the object detection as an example, this one state-of-the-art technique. If we're using the TensorFlow Lite, on a mobile phone, we use 400 milliseconds. This is clearly far from real time. Then what about if we do pruning? Because quantization is very weakly supported. So if we're going to test on the non-structured pruning, then we're going to reduce the size by 8 times with 2-point reduction in the MAP, which is the accuracy. This seems reasonable, but how to translate into the acceleration? First, it's not supported in the prior acceleration framework for the general sparsity. We have supported it, but we only get 40% acceleration using our compiler. We have built a compiler with our collaborator. If we're going to test on the filter or channel pruning, then what is the situation? Then there is a huge accuracy degradation, which is almost 20-point reduction in the MAP with 8 times compression. This is clearly not acceptable. If we see something has an accuracy degradation of 20 points, this is, although it's still better than the current work on the SSD or MobileNet SSD, but we think that this is very difficult to accept and to deploy into the actual real life. So we see that the current work on the non-structured and structured pruning are actually 2 extremes. Non-structured, people believe it to be accurate but not hardware friendly, while structured, people think that this is hardware friendly but clearly loses accuracy. There should be something missing here, something missing that we can take the full use of the hardware acceleration or the hardware parallelism, but it also can be accurate. So this missing point is actually to determine a specific regularization degree, which is the pruning scheme. We have a large amount of things to play here, because the inherent parallelism of a neural network, this is in terms of millions of parameters and in the giga order of computations, which is huge and orders of magnitude higher compared with the hardware device parallelism, even for FPGAs and GPUs. So there is a large granularity that you can play here, that the regularity can be something in between, while the hardware performance can still be optimized. And the second thing is to perform compression and train the weights, which is a pruning algorithm. We have done here, which is the ADMM-based pruning algorithm and its variants, but what is missing here? So our next, we're going to discuss a series of what we call as fine-grained structural pruning schemes that are going to solve these problems, and which are both fast and accurate. So first, what we are going to discuss is the so-called pattern-based pruning. In the pattern-based pruning, there is actually a so-called pattern library that we can see on the top. The pattern libraries are the patterns that we can choose for each kernel. And at the bottom, we can see that in actual filters, a kernel can choose a specific pattern. And then the weights on that pattern can be flexible, and the weights are not on the pattern are actually removed. All the kernel can be completely removed. So, and then we can take the other types of patterns and so on. So we need to select the pattern for each kernel or completely remove this kernel. So this is from a predefined pattern library, which this library should be automatically generated. And then during training and compression, we're going to train the weights on the pattern and prune the rest of the weights. And then we have developed the ADM-based pruning algorithm, and also together with an effective pattern library generations. Then for this pattern-based pruning, then we're going to discuss why it is accurate and also has a high hardware performance. At the theory level, this kind of patterns have a higher capability of feature extraction versus matches with the human visual systems, and also is because it is going to sharpening in the feature extraction through its coincidence with the Laplacian of Gaussian filters theory. So if we test using the standard computer vision test, we can see that with these patterns, actually we got a higher capability of feature extraction compared with without the patterns, the original neural network. So with the patterns, it's typically a good thing. And at the algorithm level, typically as long as we are going to apply the patterns, there is a higher accuracy due to the matching with the visual system due to overfitting elimination, as we can see from this ResNet 50. The question here is that, okay, these patterns may be accurate, but how do you prove that it can be fast? Because it seems that it is still irregular. Now this is where the compilers should take place and play the roles here. So then we want to ask a fundamental question, like how can we actually get acceleration? We can get acceleration when one processing element, also processing core, is going to deal with one same shape of application, a same shape of computation, like one pattern, for a relatively long period of time. So one specific processing core needs to deal with one pattern, maybe 1,000 of these kind of patterns with the same shape. And then there is really very minor overhead in this case. So the compilers can perform the code generation with the reordering and group the patterns together. And after the grouping of the patterns, they can grouping and allocate into different threads. And then thread 1 deal with pattern shape number 1, thread 2 deal with pattern number 2, and so on. And in this way, we can maximize the parallelism and also the performance for each processing elements. Finally, why are we using the 4 input patterns? Because the 4 input patterns matches with the SIMD structure of the mobile CPU or GPU. One processor core actually can perform 4 computations at the same time. So if you are using the 3x3 kernels, it needs 3 clock cycles. But if you are going to use 4 input patterns, then in 1 clock cycle, it can finish 1 pattern. So there can be an acceleration of 3 times. Or in other words, the acceleration can even be larger compared with the computation, computation reduction. Pattern-based pruning can be generalized to something like the deconvolutions, which is actually used key components in the LiDAR-based detection, like point pillars and also GANs. And we can see here of how to generalize into the deconvolution here. So pattern-based pruning is mainly used for the convolutions and for the 3x3 kernels and beyond. But there is also fully connected layers. There is also 1x1 kernels and how to deal with these kind of cases. So we have invented the so-called block-based pruning. Block-based pruning is a general pruning that can work for all types of convolutions and also the fully connected layers, including the transformers and so on. So there is this weight tensor format for the convolution layer. And then there is this weight matrix format for the fully connected layer. For the weight tensor formats, we can see that we're going to group the nearby kernels into blocks. And we can see we can perform pruning, which is this kind of gray entries. But we see that the remaining patterns in each kernel within this block should be the same. We can see that the shape of the blue patterns are the same, and whereas the green patterns are the same, and so on and so forth. So as long as we can enforce this rule, actually it can be accelerated using the compiler. In the weight matrix format, how to do the block-based pruning? We're going to divide this whole weight matrix into blocks, and then we're going to apply independent row and column pruning in each block. And then the remaining is not pruned. Through the compiler's perspective, these two are equivalent, and we can get acceleration through a unified compiler-assisted acceleration framework and a unified solution framework using the ADMI-based pruning. Block-based pruning, as we say, has a wide applicability. It is even generalizable to the 3D convolutions. As we see here, we have generalized to the 3D convolutions for the activity detection when there is a third dimension of time. And here shows how to generalize into the weight tensors. And then we're going to discuss why this block-based pruning also has a higher accuracy and a higher compiler-assisted speedup. The higher accuracy is because anyway, we are going to divide into smaller blocks and then play independent row and column pruning in each block. This is anyway have higher accuracy compared with the case when we're going to eliminate the whole rows and whole columns together. The second is that it has a high hardware performance. So to analyze the hardware performance for block-based pruning is beneficial for us to understand why this kind of fine-grained pruning can achieve the highest possible hardware performance. Because these weight matrices are very large. This weight matrix size is orders of magnitude higher. It has millions of parameters and millions of computations. This weight matrix of tensors has orders of magnitude larger than the available parallelism on a hardware device. So even if we are going to divide into blocks and perform pruning thereafter, so the remaining computation is still possible to achieve the maximum performance on this device. So and the overhead can be minimized by the compiler. As long as the hardware parallelism can be maximized, then whether we train a smaller neural network directly or we use this kind of fine-grained pruning, will having the same performance under the same compression rate, but the later will certainly be more accurate. And then this is a key observation here. So we can see that we can get simultaneously high accuracy and high hardware performance. This is not merely a trade-off of accuracy and speed. We can see in this example, which is on the ResNet 50 on the ImageNet. We are using 6 times pruning with a different block size. Unstructured pruning is essentially block size of 1 by 1 because any individual weight can be pruned. Unstructured pruning is essentially a block size of the whole weight matrix because we can only do the whole channel or the whole filter pruning here. We can see that with a proper pruning size, a block size, we can get almost the same accuracy as unstructured pruning and almost the same speed as the structured pruning. So this shows that this is not a merely trade-off of accuracy and speed, but we can exploit the advantage of both unstructured and structured pruning while hiding the disadvantage. We can achieve both accuracy and performance. So here is an overall flow of our core technology, which is the so-called CocoaPi, Compression-Compilation Co-Design. And then we have a keynote paper, which is published in the cover article in Communication of ECI, which is coming in this summer. And then we can see that there is a left part, which is the fine-grained pruning schemes, and the right part, which is the compiler-based optimizations. The input here is actually a deep learning application or a model. And then the output is a graph-based representation of the compressed neural network. So we have invented our own format for the compact representation. And then from the compiler perspective, we're going to make into an intermediate representation. And then after this, we have multiple techniques like auto-tuning, like computation reordering, support for sparsity and load redundancy elimination, tiling, and so on and so forth. Some of us is our unique inventions, and our output is actually the software executable code on a mobile. From an offline optimization part, we optimize both a neural network model and also optimize the codes from the compiler code generation. And we generated executable code or SDK or a middleware, which lies on the middleware layer of the software stack, and which can be interaction with the application layer, but it can be integrated into the application or the operating system, depends on our collaborators. And then we have an underlying mobile architecture layer that can be defined as the different mobile devices, like the mobile phones, embedded platforms, or auto-driving platforms. So we have some recent work on the joint network pruning and architecture search, which is to search both the network and also the pruning scheme to make it compiler aware, which is just accepted in CVPR, but we're just going to omit the details here, which is quite evolved. Okay. So now we're going to see that we see only the performance of the compiler. We do not consider network search. We do not consider pruning, only the original pruning, only the original neural network, and we do floating point operation. So we can see the results listed here. This has no effect of pruning. Our results, which is a so-called DNA fusion as a result here, which is actually we just accepted in PLDI. And we can see that our performance is consistently better compared with the competing frameworks like MNN, TVM, TensorFlow Lite, and PyTorch Mobile. And meanwhile, we can see we can support a large variety of models, including the basic image classification, including the segmentation, object detection, the activity detection, and also natural language processing, which is the BERT and the GPT series. We also support much wider compared with the prior work. So this is a reason that we are only relying on our own compiler instead of the prior work. And this is through our compression-compilation co-design. What can we achieve using a mobile phone? We're using this Samsung Galaxy S10, which is an Android phone, and the ImageNet dataset. We can see the results on the right. If we want to having an accuracy, which is a top one accuracy on ImageNet of about 78%, we can make a speed of 6.7 milliseconds. If we make it accuracy 75%, which is a MobileNet v3 level, then it is less than 6 milliseconds. If it is mobile version 2 level, then it is less than 4 milliseconds. If it is further, and then we can be accelerated further. So this is what we can achieve at this moment, and this is also achieved, accepted in CVPR. So this is our results to have the extreme acceleration. So we can see that ImageNet is really simple. I mean, ImageNet is really simple for a state-of-the-art mobile phone. So we need to go for more challenging technology, not to stick on MobileNet. MobileNet is very fast, 3 milliseconds or so. And recently we got 45 millisecond inference on BERT and 150 millisecond on GPT-2, which is a prior version of the very large model, GPT-3. So we can potentially achieve real-time execution of all deep neural networks. And here is the results, what we got from the YOLO-based detection of the Microsoft COCO dataset. We can see all of these are based on our compiler because we are faster than the others. And we support the general sparsity. Our results is a series of the trade-offs here. As we can see, it starts from the Euro V4, and then it has been an optimal Pareto optimal trade-off. If we compare with Euro V3 or the tiny versions or the SSD, we can see that we can simultaneously be more accurate and also can having multiple times speed up. So we are simultaneously more accurate and also faster compared with training small models, even if we are using the same framework. This shows the effectiveness of our compression. So if we are going to see the LiDAR-based auto-driving systems, we see that the original neural network is even more redundant. The original point pillars, if we implement on mobile phone by our compiler, we got over 500 millisecond in inference. But actually, it is too much. They don't consider the performance too much. So even if we reduce it by 15 times in the number of computation, actually our average accuracy can even be higher than this work. And then we can get a speed up of 97 milliseconds. And then we can see that this is almost real time because this kind of LiDAR, typically it is 8-10 frames per second, this kind of speed for auto driving. So this is the overall results we can get for the compression compilation co-design. Previous table is only the compilation, and here we got the effect from the co-design, and this is measured on the Samsung Galaxy S10 under the same accuracy. We can see here, to a large extent, we can achieve real-time performance. As long as it is in the order of tens of milliseconds, can be said as real-time. This kind of values, this is for 16 frames. So for each frame, this is only 6-7 milliseconds, which is clearly real-time. And natural language processing, typically the real-time requirement is a little bit loose, to hundreds of milliseconds, 100, 200, typically okay. So the only thing that we are not real-time is faster RCN and masked RCN. These two segmentation techniques we cannot achieve real-time. But of course, we are the only one that can support them because none of the prior work can support. Another thing is that actually it can be replaced by UNet or ULECT for the more efficient segmentation, which we can achieve real-time. So if we compare with the other software frameworks, like the competing frameworks, TF-Lite, Tensor TVI, and MNN, and so on and so forth, we can see we can support much wider model coverage and mobile CPU, GPU coverage. We can achieve a average speed up of from 5.6 times on average to more than 14 times on average. So our speed, if we call it over very fast, then all of these are either slow or very slow. And because, as we can see previously, we can achieve real-time on most of the cases, and if you multiply by 5 times or to 14 times, their framework cannot be real-time. So they can only deal with images, but we can deal with videos. So if we see the breakdown of improvements, a compiler itself will get 50% to 3 times speed up. And the pruning scheme and the algorithm will get 2 times to 10 times potential speed up. We say potential here because this speed up cannot be realized without compiler support. With compiler support, these two speed up can be multiplied together, and on overall we got 3 times to 20 times the actual speed up, which can towards real time and the best effort acceleration using the edge devices. Not only we can outperform the prior software frameworks, but we can also outperform the hardware accelerators, dedicated hardware accelerators. Here are the energy efficiency and the speed compared with the prior work, like the Google TPU, like the Iris, like NVIDIA Xavier accelerator, or some FPGA solutions. And we can see that our mobile phone-based framework, even if this is a software framework, but still can get a much higher energy efficiency compared with those dedicated hardware frameworks. So if we are going to compare with all the prior FPGA solutions, we have brought all the prior IPJ solutions as long as they report the energy efficiency. As we can see, they are all here from the prior work or from the IPJs and the hardware conferences. And if we compare our results using a mobile phone, we can see that under the same accuracy, we always consistently has a higher energy efficiency. And the gap is not minor. So we want to explore why this is the case, because conventionally people believe that dedicated hardware should be more efficient, but we show that this is not the case. Our framework is more efficient. So, but this is surprising. So what is the reason here? So in last year's stack paper, we did a comparison like in this way. We see that so what the x-axis is actually the error rate, and the y-axis is the energy efficiency. We are starting from the same neural network, so same recurrent neural network. And with pruning, of course, we can get tens of times energy efficiency compared with those IPJ work. But suppose that if we do not have any pruning, our model are the same as the prior work. We don't even use quantization while the prior work uses quantization. Actually, we can get 88% energy efficiency if we do not have anything like the pruning. We are having the same framework and the same model. So this is a little bit surprising because you may say that, okay, so this is because of the pattern-based pruning, block-based pruning, ADM-based algorithm, but it turns out that this has nothing to do with all of them. This is only to do with compiler and the mobile phone, and the energy efficiency is almost the same as an IPJ. So of course, the compiler will play an important role here because the compiler is much more efficient than the prior work. But more importantly, actually, the mobile phone itself is very energy efficient. Mobile CPU and GPU is actually the driving force of the technology advancement. Nowadays, only the mobile phone CPU and GPU can use 5 nanometer or 7 nanometer technology node, while the IPJs or ASIC cannot. They use 22, 28, or 40 nanometer, which is the best what they can do because they do not have enough manufacturing compared with mobile CPU and GPU. So mobile phone itself is energy efficient. It's just people believe previously it has limited support of the models. It cannot achieve real time. So people do not recognize this. So if we say that our framework can achieve a higher accuracy, it's better to say in the other way, to say that our framework can relieve the potential, the high potential of those kind of mobile devices and to make it actually having a great potential in the future. So if we can see some of the actual demonstration of the real-time AI on mobile phone, we see some simple one first. This is the automatic style transfer that the input is actually is measured in last year this time, which is before COVID. So this is 1 year ago our capability. And then resolution upscaling. This is a large companies, many companies are very much interested. So the input is a low resolution video, and then from upscaling we become a high resolution video. So this is not only useful here, but some companies like AMD or the smart TV companies also, they want to use it for their applications, not only on the mobile phone. And this one is automatic coloring. Input is black and white, and output is a colorful videos. These are easy to make it real time. So for the YOLO wave 4 object detection for the auto driving, actually what they can do is typically something like this. But we can see that on a mobile phone. Of course, no one will use a mobile phone for auto driving, but we just see that there is a high potential here and similar as this kind of object detection. 3D activity detection is something that we have heavily optimized. And what we can achieve is 6.8 millisecond per frame using our framework. Nowadays is outperforming the prior work by 40 times speed up. So we have some other things like the real-time open pose. That is the pose estimation here. And then the real-time BERT, which is a question answering here. And the real-time the neural talks, which is the giving an input or a video, we're going to having translated into a sentence. We also having the samples of segmentation, medical devices, and also the hand gesture and so on. But the issue here is that because we have at the beginning, we're sorry that we deleted 2 pages of the demonstrations, but you can find the demonstrations on our YouTube channels. So here are the media coverage of our works, and including some other works like the adversarial AI, and then our acknowledgement from the government funding that we have got, and also the industry funds and gifts. So thanks for the collaboration here. And also, if you are interested, please welcome to our YouTube and Billy channels. And then we are keeping uploading the new videos, new applications. We are quickly expanding and trying to generalize to all the applications and all the devices, from the microcontrollers to the high-end GPUs. I think we've tried to make a general unified framework for a full AI stack. Thank you very much. So please, if there's any question.
Thank you, Yanzhi. Thank you for your very excellent talk. And so, if the audience, if you have any questions, so you can input your questions at the Q&A box. So I can ask a question first. So how about how do you think about the role of the quantization in your framework? Right now, you just consider about using the pruning.
Yeah, actually, this is a very good question. I personally, I would think that quantization has an important role as well, but the important role is in terms of the DSP and the NPUs. So the mobile phone currently are mostly equipped with the DSPs. Several versions ago, those DSPs are not accessible because this requires to do some decoding work and for the OFDM and other things. But nowadays, those kind of DSPs can be programmable. So that requires the quantization. If you ask me that whether quantization will be helpful for the mobile CPU, I will say it's better not to use a mobile CPU because it will slow down your main activity on the mobile phone. But in terms of DSPs, this is a requirement for quantization, and quantization needs to be very reliable there. Yeah, this is my suggestion for quantization. But the issue here is that quantization is a technique that is theoretically good, but in practice there is a big issue here. If I publish paper, then actually I have quantization results of 4-bit quantization for the BERT. But in practice, I know that even if I use 16-bit floating point for the BERT, it's still not accurate. So there's a big gap between the theory and the practice when we consider the actual demonstration and the practice. Yeah, so I think for quantization, there is something that is hidden there. Yeah, one needs to be more clear. Yes.
Okay, thank you. And so I have a follow-up question. So in that case, so currently in your framework, so you still use like the 32-bit floating point?
We're using 32-bit floating point or 16-bit floating point. Yeah.
Okay. Even
and on the support. Yeah.
Okay.
Yeah. So is there some question? But I don't know why I cannot read it. So if you can read it for me, thank you.
So if the audience have any questions, you can input your questions in the Q&A, or
you can directly ask. Thank you.
Okay, so yeah, or someone, can you paste the link to the YouTube channel?
Oh, can you paste it?
This link.
Yeah, please like our link. Please subscribe.
Yeah,
our link.
I think in the I think you already gave me the link. Send me the link, right?
Yeah.
And I will also I think in my previous email to our department, so in that PDF file we already have include the YouTube link there. Okay. So one audience asked, would you please compare the pruning to the NIS? Hi, Yanzhi, you're muted. You are still mute.
Am I okay? Can you hear me? Yeah, actually, this is a good question. This is typically a question that we typically encounter when we are doing the presentation. So first, our work is orthogonal to NAS because currently we have took some efforts on the combination of NAS and pruning. And then if you say that our work, because it's pruning, and we can make it compiler aware, and NAS is not compiler aware. So of course we get more acceleration because we have a specific compiler. But actually NAS can also be compiler aware, which is we also do it. So I will say it's like this, depending on the case by case. I will say because our method is more flexible, it's more fine-grained. So typically, if you only use our method, suppose that you can accelerate by 3 times. Then using network architecture search, you may be accelerating 2 times. So it should be higher, but it can be combined. But combined is not 2 multiplied by 3 by 6. This is not, you cannot imagine to this. But this may be 3.6, 3.7 times you can anticipate in this level. So they can be combined. They can be make it both network search and pruning aware. But another thing that we want to, so our advantage is a fine grain, but it can be combined. So this is a general conclusion. But there is a following up thing is that suppose that if we want to help the customers, then typically we shouldn't give them the choice to do network architecture search because it's too much time consuming. And then network architecture search is very difficult to be actually automated. Still in our practice, I mean, we claim that we are automated, but still there's a lot of hyperparameters or the manual tuning stuff. So I would suggest to do the combination, which to find the Pareto optimal trade-off of the accuracy and speed up by effectively combination of the network search and also the pruning search. And in this way, so if someone asks, and then we can have this APKs or this kind of Pareto trade-off and of this kind of models and applications. I would suggest to do this and to compute in prior instead of to search as long as there is need for a new model, because the time is a big issue. Yes. How do you measure the running time? Yeah, this is actually a good question. How do you measure the running time? Actually, when we build our sparsity supports, we support general sparsity. We support a non-structured pruning model as well. I mean, because non-structured pruning is essentially a block-based pruning with a block size of 1. So it has no problem to support it using our framework. It's just we cannot get much acceleration. If you want to use our, this is a problem of to use our tool compared with TF-Lab. Yeah, our tool is difficult to use. Nowadays, even in our group, there is a limited number of students and that can an engineer that can actually use our tool. So our tool, because it's a coupled tool of the compression and compilation, so generally it needs 2 people, one working on compression, another one on compilation, and it has something that is not fully automatic. This is a big limitation of our current implementation. If you say that using TF-Lite or PyTorch Mobile, then it is more convenient. Of course, there is also limitations, but they are more convenient. But actually, because if we want to have a good performance, we need to support more operators. We need to support the combined optimization and search and pruning, and we need to support the more dedicated optimization on the neural network. So I mean, we plan to make a releasable tool, an APK series that is can be used, and then let the public to have a test for some applications at least. I mean, in 2-3 months. I think that we are going towards a fully automatic tool, maybe in 6 months or so, or in less than 1 year or so.
There's another question in the Q&A box. Can you see that?
Yeah, I have replied these questions. Yeah. So actually, currently the best tool in our understanding is Alibaba MNN. This tool is optimized better. Yeah, and it's not like the TensorFlow Lite, which only supports TensorFlow, or PyTorch Mobile, which is, come on, PyTorch Mobile. I can find a slower tool. I mean.
So there's a question in the Q&A box. So do you experiment with different block shapes for the pruning? I know you mentioned the size of the block was because it matched the hardware, but was there any effect from the chosen block shape?
Actually, this is a good question because, as you know, that the chosen of the block shape is not that difficult, and we can support different block shapes, different size for different layers. Actually, the chosen of the block size is doing. We have a training-free framework. It's like for each of the layer, because we want to optimize for a smaller block. So typically we have a modeling, or we can compile it and run on mobile phone, and then we can see that, okay, if for the if we just shrink the size, and then we can accelerate to the speed of 1, and then now if we only have 10% degradation, and then we're going to allow for 10% or 20% degradation, and then we're going to find the smallest block accordingly. So generally we choose the block size in this way, and it may be different for different layers.
Okay,
so typically we don't want to search this because the search is already complicated. We want to search the different pruning schemes for different layers and the original structure in different layers. This is already quite complex. We don't want to make the block come into this play as well. Yeah. So is there any questions?
Okay, so if we don't have any other questions, so that is the end of today's talk. So thank you so much for Yanzhi for your excellent talk. So it is really very, very impressive. And so your the talk from the Yanzhi will be posted on the YouTube, and so I will send all of you the links once I upload it to the YouTube. And thank you again. So thank you so much.
Thank you
for this talk.
Thank you. Have a great day. Bye bye.
Okay, thank you.
Thank you.
Thank you, everyone. Thank you for coming to the talk. Bye.